spill here.
Yeah.
Didn't record that.
Not important.
Space bar. There we go. Okay, so yeah, this is just an overview of what we're going to talk about tonight, mostly navigation, sensor fusion via common filters, computer vision, and quantum vision-based navigation, and we'll have some questions at the end. So it's about me. I've been working in this town for Norfolk Defense about 5 years. I've been in a few jobs. Most of them, since Lidos, actually have involved vision-based navigation or navigation provides in some form. Like I said, professional focus on robotics. I do a lot of AI, ML stuff, a lot of software architecture, but I do a lot of things. My current job, I'm a lead software engineer on a high-speed, small UAS drone prototype. So do a little bit of everything. Finished in 2020 here at UAH with a degree in electrical engineering and a minor in computer science, and I'm finishing my master's in EE hopefully this year. My research is a lot of neural network and system dynamics type stuff. So, after my little LinkedIn resume there, what I actually hope to do tonight with y'all is really just give you an overview of some basics of navigation. The main need of this is going to be sensor fusion via common filters. Has anyone ever heard of common filters in this room? Used them? A couple people? Okay, I'm going to go through some of the math of it, I'm going to go through some intuition of it. If you've never seen that, then I apologize in advance. It's kind of nasty. We're going to talk about computer vision and eventually tie it all back to vision-based navigation, putting this all together. You're not going to walk out of this room an expert. I'm not an expert on this either, but if someone starts saying these words to you in the future, you're going to know something about them. So, navigation theory, that's a fun one. Start off with what navigation functionally is, and it's a study that focuses on the processes of monitoring, controlling the movement of something from one place to another. Like your GPS here, I'd like to think of navigation as understanding what's around you, where you are, and how that relates to where you want to go. It's the navigation part of guidance, navigation, and control, but we're not going to be talking this time about actually enacting that change. That would be for the controls engineers, things like that. This is going to be very much focused on understanding what's around you, what's happening, and where you actually are. So navigation, going and continuing that. There answers questions like where I am and how fast I'm moving. There's a number of sensors and approaches to figuring that out. Sensors that get your position, speed, acceleration, attitude, orientation, and that other stuff. So all this stuff's a little later. But I use GPS, star trackers for celestial navigation. I've done some of that at Lidos. That's pretty interesting work too, and optical type stuff. And then it goes into this. And this is not comprehensive as far as what all types of navigational systems. There's constantly new ones coming out as we get new sensors and all sorts of fun things. So taking all of this and having these sensors, doing all that. We're going to move into something called SLAM. Is anyone here familiar with SLAM? Is this a new word for everyone? Okay, a few people here. Sensor simultaneous localization and mapping. But basically, it's a way if you have something like a robotic system or a car to take all of your sensor data, all of your mapping and localization, and put it into a here I am. So it's like what is my current position? How am I oriented? What's around me? What's the map of what's around me? Where have I been? All built from this sensor data. It has data association, and there's many SLAM algorithms. This really should be a lecture onto itself, so I'm not doing it justice for this. But it also has data association, so you can track previous features, and you get basically a semantic understanding of your map. So if you go, if I walk through this classroom and start looking at these desks around me, I've formed a mental map of, oh yeah, this is it. And if I come back in, I know, oh well, that's where that table was. Don't walk into it. So it gives you that. It gives you state estimation, as those common filters, and it gives you loop closures. So like I said, when you come back to an area, you kind of know what's happening. So going from there, I thought I had an interjection slide there. I guess I did that. I copied that. Okay, that's not supposed to. Yeah, that's supposed to see that one yet. So as far as sensors and navigating from sensors, this is kind of a better list of the type of sensors that exist and kind of the description and what states they care about and what they give you. Inertial sense sensors like accelerometers and gyroscopes and magnetometers, they give you change. As you're moving through a space, how much is something changing? How much are you accelerating? How much are you moving in a specific vector and orientation? versus a positioning sensor, which is giving you are located here. And then you're saying that like range and depth sensors, ultrasonics, LiDAR, radar, gives you how far out is something, environmental context sensors, barometers, temperature, humidity, what's it like in that map around you? Because if you're trying to navigate and make a navigational speed through something, it's maybe worth knowing that, wow, this area is really hot, the floor is lava problem. And odometry and motion sensors give you how fast your wheels might be turning in your car or on your device, and that gives you a more direct motion. So, and these are, again, some of the common approaches to navigation. You see LiDAR-based GPS, radar, IMU. They all have pros and cons, which is where some of the sensor fusion we're going to talk about here in a bit comes added there. LiDAR can be very accurate, but it can be very expensive, and it can struggle. Cameras come into all of this. Radar works well in all weather conditions there, but it has lower resolution than some of these. GPS, we've all seen how accurate GPS can be, plus and minus 3 to 10 meters. So if you're doing precision positioning, that's not always the best way, but it's incredibly reliable if you're outdoors. If you're indoors, it doesn't work. This is my experience. And IMU works well for figuring out what you're doing, how you're moving currently, but it gets drift over time if you don't have references and mapping. It needs frequent calibration or fusion with other sensors because it doesn't have a static reference, like a scope of where it is. It just knows kind of what's happening around it at the time. So that takes us to sensor fusion. I'm kind of hinting at this there, but sensor fusion is this really fun idea, fun if you like math and data flows, of taking all of your sensors, like on this list, and putting them into one algorithm. So you get the best of everything, ideally, you don't always get the best of everything. And that can be broken down into complementary fusion, so you're combining it to enhance the overall capabilities. So you have GPS for your position, but you have your IMU telling you, okay, I know I'm accelerating this fast. So now you have a better scope of where am I and how am I moving. You can have redundant fusion where they measure the same property of I'm moving this fast per my GPS measurement. My accelerometer says I'm accelerating this fast. I'm integrating up to that. My wheel odometry is saying I'm moving this fast, and it gives you a more accurate. Because you take out is it a hardware sensor dead? Does it have a voltage fluctuation, that type of thing. And there's cooperative fusion too there, so you get things that are not possible with traditional sensors, LiDAR and camera for object recognition in autonomous vehicles. Common techniques for this are the Kalman filter and the extended Kalman filter if you're doing anything nonlinear. We won't derive that tonight. I tried to, I decided that was too much. But it's used for estimating a system state by combining noisy sensor data. So you're fusing your GPS and IMU into a navigational filter. Particle filters are another way to do this. I don't derive that, but they are an alternative to Kalman filtering, where as opposed to having a model where you start to filter and fuse, you try a lot of different guesses and then condense down to a hypothesis. It's very computationally expensive. I've actually had things give me terabytes of RAM requirements before. And the neural networks and machine learning now also are in this vein because those networks are very good at running complex relationships. And if you put 30 or 40 sensors on something, that's a complex relationship of what does that look like? Because every sensor has different bandwidths, different things it sees. And we'll talk about that when we show some cameras later of the amount of different cameras alone you can get to. But moving on, moving into this. Like I said, so a Kalman filter is a recursive technique used for estimating states of a dynamic system. It's a relatively efficient approach if you have a good model. If you don't have a good model, it's going to be difficult. Tonight we're going to look at the linear Kalman filter. This is only good for linear systems or systems you can linearize. So if it's nonlinear and you're doing something more based on reality, the extended Kalman filter is what you're going to deal with. And I'll kind of explain the difference between those when we get through this. But this is I like this picture. This often I didn't make this, but I like this picture because it really, I think, rapidly shows what a Kalman filter is supposed to be doing. Starting at the left, you have the blue color. Hopefully, people are not the green color here. And you're making an estimate at your last time step. You drive down the road that I'm at this position, moving this fast, and you have two states now. You have your prediction and you have your reality. And from there, you advance one time step, estimated K, probably should be estimated T. You estimate K, And now you have two states. You have what you're at now, and you have your previous prediction. You can then start to pull where you're at and compare that with your prediction to update your prediction for the next time step. So you're recursively going, I think I'm going to be standing here in 1 second there, and then see if I'm still there in 1 second. And if I'm not, I need to take that and go, okay, what's the difference there? How far have I shifted, and update my prediction for the next step from there. So you start to get this, and we'll kind of see as we go through the algorithm a little more in depth there. But this is a good example, and it shows at the bottom, like the green curve is in the middle where the wheel odometry and the inertial navigation thinks it's going to be, but it's a little, behind where the GPS and LiDAR say it's going to be. But if you fuse all those together, you end up with this, I think I'm in this range, and these are probability distribution functions there to say, hey, I'm confident that I'm fused into this chance of being in this window. So this is more of an algorithmic view of what you're looking at for the filter. You start with your initial states, and that's timed at x equals 0, basically. You go into your filter in this box, and you look at the previous states.
Way. Which button is it? Big button is laser. You're the wrong way. Oh.
Whoa, look at that. Yeah. So you start here at your previous states. So this is x equals 0. So you advance 1 time step. And now this is looking at your previous states and previous estimates there. You're going to use all that information to predict what's happening now. And from there, you're going to update everything. And we'll go into the math here in the next few slides there. And that update's going to include your current measurement. So you're saying, give me your predictions, give me a measurement to see how wrong I was, and then update everything and get some outputs, and then advance the, recursively go through that cycle. Yeah, so here we go. So the initial state here starts, and you're basically saying, I have a system, that's what that slide is supposed to be. I have a system, of AX plus BU plus W. A is a model of your system. B is your input to the system. This is getting into linear system theory, if everyone has some familiarity with that there. But this is basically just describing how something changes with respect to time. So A is your model, B is your input, W is just noise associated with your system. This is just, you get that for free by living in the universe, basically. But this is your last real state, and this is, you're starting here with x equals 0, you have state. Moves into your previous state, and now your filter algorithm is going, oh, okay, my last known state was basically what was put into the input. So now, we're going to have these two equations here. This x hat of k, the bar is not in that, but that bar there in the exponent for that represents the prediction. So if you see this p minus x minus and the exponent, that means that this is an equation of your prediction of states. So that says that for the state k, your predicted state k, that you're looking at the prediction from the model plus your input. Now I probably forgot what happened here. And then the second line is the uncertainty. This is a probabilistic function, this guy is, and it is saying that this is how probabilistically certain of my estimate that I am, because this is all a probability scheme at the end of the day. So from there, so you have that predicted state, and then now you're going to update those states. Okay, this is like a fun. So this top line here, this case of K is called your common gain. This is basically weighting out your new your measurements with your probabilities and all your noise and saying, okay, what's my actual weight based on how I defined my model. This year, then you're updating all of this there with your common gain, and this H is your measurement, so you're pulling that back through here. And finally, you're getting a probabilistic down here that's the uncertainty of the, you're updating everything here. And then you basically just tie it back through a bit, and that's at a high level. And yeah, I know that was not a good explanation. This is a black art of a field anyway, but this is a better view, I think, of how you would incorporate this into a guidance, navigation, and control flow. You would get a from the outside a position, speed, and orientation. You get your random measurements. You don't have to use a low-pass filter, but if you're measuring raw data, I highly recommend it. It makes life a lot better. You have your navigation filter. Again, that can be a particle filter, that can be DKF, that can be any number of things, but for this purpose it's a KF. That goes into your control loop, which has been given a set point from some operator, some scheme there, which all loops back to have a physical outcome. If it's a plane, that gives you your roll pitch yaw. Do you go faster? Do you go slower? The same way your cruise control in your car works, basically. So yeah, so we'll do a little example of this there. Maybe numbers make it make a little more sense. So we're going to think about a car, the model of a car. This car, we're going to model in two states. It's position and velocity, so x, y, and vx, vy. So we're going to assume a time step of 1 and a constant velocity model. So like I said, you have x, you have your model here, and then just some noise that you just get for free. We're kind of going to neglect that because all it does is just add a Gaussian distribution on top of this there. But basically it's all constant models, so x, constant position of x, constant velocity of x, and then cascading through. You've probably seen this in linear algebra and physics to some degree there. So then what we're going to do is we're going to assume this car has two sensors on it. We're not going to have just one, we're going to actually try and use this. So it gives you, this Z here is your, basically your sensor measurement, or like what the filter believes your measurement to be there. So it takes in measurement plus measurement noise. The B is supposed to be measurement noise, and then the measurement is an H. So you get all that. For this matrix here is going to be your actual how you define your sensor, and this is something you define when you make your model. And I'll go more into the model part of this too, because that's where this breaks down from a application standpoint. Is having a model, and this is more noise, that like uncertainty associated with how good is your sensor, because no sensor is perfect. You have to model that too, and go, okay, I know that sensor 1 here is basically half as good as I want it to be. So you have an initial state. We're going to assume the initial state basically just everything is essentially zeros and ones. Take it easy. So the first sensor, we're going to roll through all those equations that we were showing up here. Yeah, these equations, the prediction and the update set there. And that basically gives us that, okay, this first state predicted by the filter for the first sensor is this. This Y here is kind of the output of that. That might make a little more sense in a second here. We're computing a Kalman gain out of this, and then this here, this X predicted state, is what it thinks the predicted positions are of the filter of the vehicle given that one sensor. So it thinks that its initial condition was 1, 1, 1, 1, straight ones, and it predicted that it's a 1.12, 0.9, 1.6, 0.97. So then we go and repeat the process with the second sensor. You run through the same mathematics, and it's very recursive. And this time you compute the gain, but our state here, notice it doesn't have a subscript anymore. It's just X. Is going to be the previous state we computed from the sensor plus this new one, this Kalman gain times that Y we just computed. And that gives you, this is basically your final output. Now you've had two sensors. So it's fused everything together, and if you notice, your values are much closer, 0.99, 1.0, 0.99, 1.0. So by combining these two sensors and making these assumptions up here, we are able to get closer than we were here. You see you have a higher variance, 9.7, 1.12, all that. By making these assumptions with these sensors, you can fuse them together and actually get a solution that is more accurate. And you might think that this here is negligible values compared to these, and in this case it is, if we're assuming that that's probably like inches or centimeters or something like that. But that could also be something where you're working in a logarithmic space, or that could be something where you're looking at miles. It would be Mars orbiter problem where half the team was an imperial and metric. Those values actually matter. And someone that had worked in some precision munitions before, this is the difference between hitting the tank and not hitting the tank. These numbers are. So you do actually care about that. So some pros and cons of these there. Very good for linear systems. That car was really moving in a linear fashion. If it was taking, if it was accelerating wildly and was, up and down and not something you'd like to model, this would break down. It's pretty efficient because of the recursive approach. You can really get into some fun CS stuff. anyone that's done recursive programming, solve the Fibonacci sequence recursively can kind of talk about that. Because of that, you can really get into some high-speed stuff. It can also lend itself to some low-level embedded applications because of that. You're getting down into assembly and things like that. It handles uncertainty really well because you're fusing all your noisy data, and I don't know how many people here have taken the random signals and noise in the W department, but they talk about that if you put all, when you saturate something with enough noise, it kind of just becomes a flatline white noise type. You kind of just, it all falls out. Because it's recursive and you're only storing the previous state, it's pretty minimally efficient from memory-wise. A particle filter in comparison will generate, 10 to the 6, 10 to the 9, 10 to the 12 particles and make, 1 billion guesses. And, I've had MATLAB be like, oh, you need 300 gigs of RAM to generate this model. And that's not viable on an embedded computer. If someone thinks it is, please let me know. I actually have some job offers for you if you can find that. It's widely used and well understood. It's been around for a while. I think the original papers of this came out 40 plus years ago. So there's been a lot of time for that mathematics to mature, and that's why there's new variations that handle these nonlinear cases now. Some of the cons is, this one is limited to a linear system. It does, but if you go to the extended common filter or the unscented models, you can get around that. The difference between the extended common filter and the linear in a simple description, is the extended filter takes a Jacobian of your linear dynamics, and as opposed to saying, oh, I think the car moves in a simple algebraic way, you're now kind of making a differential equation, taking a Jacobian of your dynamics matrix and iterating over that from a state perspective. So your model becomes more complicated, but because of that, you can capture the rich dynamics that show up when you actually take Jacobians and take derivatives. But taking the Jacobian of like an F22 is something no one is probably capable of doing, at least not in this room. It requires an accurate model. No matter what common filter you do, this is all based on your model. If you can't model your sensor well and know like this is what it's going to break down, this is how I'm moving in some form. If you're making guesses, that's a particle filter does do that better. For very large models, if you're dealing with something with 100th order dynamics, this is going to be computationally inefficient. Sensitive to incorrect noise assumptions. If you make an assumption that your sensor is worse or better than it is, that may throw off everything. And it's difficult to tune. This is a black art, and people who are good at this make a lot of money in this town. Actually, any town really. Going from there, hopefully by now we talk about and go into this vision stuff now, this computer vision, you can start to maybe. The point that I was trying to get with this is to think about is as we talk about computer vision and move forward, what that means in the context of a navigational filter. So it wasn't just completely a waste of time. So starting with vision navigation, computer vision is, I guess, a relatively new field. It's only been around for decades and decades yet. AI is something you can call it, but it also has non-AI, non-machine learning algorithms that have been around for a while. But it is an approach that allows computers to recognize and analyze and interpret visual information as opposed to just your GPS sensor saying you're at XYZ decimal points, or your accelerometer saying you threw me on the floor, here's how many G's I experienced. This can be done with both machine learning and non-ML algorithms. Yeah. So here's an example of what computer vision looks like. This is an edge detection algorithm. What this does, this looks probably like a Solver algorithm there, but what it does is it saturates, and a lot of these will convert English to grayscale and try and get this sharp outline. Because if you're doing something like an object detection or something like object tracking, this is this is a more defined shape than this is with all the colors. There's just less information, and the information you pull out here is more striking, especially if you're trying to be driving in a car and go, is that a stop sign? This is an easier thing for the computer to understand than all the noise and colors and all this, but you can still deal with that. So, And this is also something, you know, if anyone's ever seen Terminator, this is the opening of Terminator basically. You have all the bounding boxes and, you know, you can track them, you can identify them, and they go off screen. Ideally, you can come back and still know what they are. But when you combine these, you can start to, I've done this, some of this professionally, you know, taking edge detection like this and combining it with this because it's easier to classify the right than the left, basically, when you look at algorithms. This is just a touching on what computer vision can do. Yeah, so now I'll just, you know, show for OpenCV2. If you're doing anything with computer vision and vision-based navigation, you will be using this. Highly recommend this. It works in almost any language. It runs on any type of computer at this point you can possibly do. You can reinvent and redo like the algorithms to do this stuff. I've done it before. It's part of schoolwork, but just don't. This is optimized better. This runs on board. This can run your GPU too. Every piece of vision-based navigation I've worked on involved OpenCV and Torch Vision, which is, you know, connected to this too. The other thing that I'll talk about briefly is a lot of these techniques now, like this in particular, is done with machine learning networks, they're done with deep networks, convolutional networks. You can do this without those. They're slower, but I've done them, you know, again, professional as a hobby. You know, this type of bounding box, you can do it without having to go into machine learning and proper deep learning. But it's more accurate to do it with a deep network. This is mostly because the deep network can understand complex relationships, especially as things move. When you do something like this without it, you often end up looking at edge detection and then going, you know, if that's an artificial edge around this car, that must be a car, but it doesn't gain understanding of the car frame to frame. You know, something like a convolutional network and deep networks can actually follow this in video and go frame to frame. That's the same object. So that's why, you know, that's very ubiquitous now. And when you do anything with vision-based navigation, you pretty much always run into machine learning-based because of that. Because, you know, this is your classic problem. If you're at a stoplight with, you know, your Tesla Cybertruck and it has to decide who is running over first. So, yes.
If there's enough of a reflection on one of the vehicles in this situation, could it give a false positive of like a third vehicle? Of like a reflection on another vehicle?
If you believe the, you know, yes, it can. I mean, and that's where some of these stuff like edge detection mitigates that actually. Because if you think about it, the edge detection off of this is, I mean, it doesn't have, you know, assuming this is like a car, right? Assuming you're looking at that. If you filter that out and just look at the edges of your car, you know, like one of you walkie pickup trucks, it just looks like a square, then it's going to look like this. So any of the reflections on the metal are not going to show up there. That's going to be more like a surface thing. So it can go, oh yeah, this is, you know, like a blocks there, and not think it's another car. But, you know, I've also seen videos of like, you know, and if you've never seen it, you should look it up there, of what a Tesla thinks a train looks like going across the track, stopped at a light, because it literally will show you just like a truck that's been stretched and elongated, and just like semi-truck there. So it doesn't really infer like that's a train. It doesn't know that. It's just it's like, this is clearly not a sedan, so it must be a truck, and it just stretches it like, you know, like taffy. It's really comical, but and it says a lot about what they're doing with the algorithm internally for that. OpenCV. So, you know, kind of moving into that space there. So vision as a sensor. So we talked about sensors quite a bit there, and we talked about how to use them there. So let's think about, for a little bit, using vision as a sensor and how we can think about that. The main motivation here is, you know, looking at all the sensor types we had previously, some time ago. This gives us a different view of our current state. And it's things we really can't measure from a traditional sensor. You know, if you look at like a GPS or an accelerometer, things like that, these are not really things that like those are not capable of understanding the complex relationships in visual scenes. That's like what, you know, I was just talking about. You know, you can't look with a, you know, the GPS or the radar, the LiDAR can tell you this is around me, but does it really interpret like the complexities around that, or just there's an object? You know, if I have a LiDAR sitting here and shoot it that way, does it know if what it's hitting over there is a wall or a table or a person or, you know, anything at all? versus, you know, like I was saying, a deep network that can think about this and go, oh, well, you know, semantically, you know, that's a person moving around. Something else here that, you know, I'll show for is redundancy, because your sensors do fail, especially when they get sent to countries that have a lot of sand or bad weather. And even just normally, because that's how hardware works. The other thing that is GPS denial and GPS denied navigation. That's something that if you work in this town in navigation, you will see that term a lot. And some of you probably have seen that term floating about really everywhere now. I don't think I've seen a contract in the last 5 years that didn't have GPS denied navigation as part of it. That's functionally just, if you're flying over an area and, you know, a opposing force says, we don't like things that can communicate wirelessly anymore, you have lost GPS, and it's very easy to jam things like that, especially if you're indiscriminate. And vision-based navigation, because it doesn't rely on outside signals, it just relies on what you can see and what you've mapped, gets around that. We had this really cool project at Lidos where they show off a sensor pod where they could, you know, fly basically like over, I think it was something like Australia, I think it was in Dominica, but they were flying over Australia and they went out over the ocean and they turned off their GPS like as soon as they hit like the shore, and then they would fly out for like hours and they would come back in and the vision navigation would go, oh, I know my map, I know where I was, and can pull that back in and could basically pick that up. And it was supposed to be like, hey, oh, well, you know, what happens if, you know, you're doing that, you know, think again like a military aircraft there, you know, you're flying around Ukraine and Russia says no. Can't get any GPS signal. This is a way to get around that. But you know, going from there, vision sensors are really just cameras. But you know, and this is why this matters, is because what does vision actually tell us there? This is the same image from 6 different observatories there in different wavelengths, basically: radio, infrared, visible, ultraviolet, low energy, high energy X-ray. And you can see that each picture you get different details. Same with this one there. This is the Milky Way, different wavelengths there, you know, like, and you can see different details come out there. So you can already start to go, you know, like, oh, well, you know, you had all of those sensors before. What's stopping you from adding, you know, infrared, near infrared, optical, X-ray to, you know, your sensor pod 2 to get a better grasp of that? And you're combining that now with, you know, the computer vision, with the edge detection, all of that, to get this complex thing. And this is going into that. Cameras are actually complex. Now, for the bit, I'm not a camera person. Not an optical engineer, I just know enough about cameras, probably a little dangerous. But it's not just what's in your phone or your webcam, you know, just a single you know, red, green, blue. You know, you have stereo cameras, some of the phones have that now where they can actually have multiple lenses, they get that depth of perception. You have depth cameras, you have a lot of IR stuff, you have event-based and omnidirectional cameras. And the omnidirectional cameras are useful for star tracking. I've actually seen that used. You can put those on top of a vehicle and get a full hemispherical view of what's above you. And then what, you know, each of these gives you kind of what you get from it. You know, a red, green, blue image might give you really good scene understanding and semantic segmentation because it can go, oh, I'm walking through a room, you know, or like, better yet, I'm driving down the road and I see a bright red object. I know red is a color that I should be concerned about as an automatic driving car. That's probably brake lights or a stoplight or something I should care about. Same with yellow, same with green. But grayscale imagery gives you edge detection, feature extraction, and, you know, efficiency because you're not processing the whole matrix of color. You know, you get depth map, you get optical flow, pixel motion between frames gives you velocity estimation. You know, that's something you don't think about is how much your eyes give you just going through the day. But optical flow can give you that same thing. You know, how quickly, if you look frame to frame, have you traversed it? That's in speed measurement. That's a position measurement now. So you can start fusing that with, you know, your other, your GPS, your accelerometer, things like that. So, and then you can, you know, again, key points and features, object detection, segmentation, pose. You can basically just keep going down this rabbit hole of what can't you do with cameras at this point. So, and this is, you know, kind of going back to our algorithm before. You basically can do the same thing of you take your raw camera feed, you process that data using edge detection, you know, using all of these techniques, and it flows right back in it. And then you can start fusing it and going, oh, hey, you know, I have all this data, I can kind of put it all together and go, you know, here's a combined state of position, you know, where I was going, where I've been, the IMU, processing your vision data, and each one of those is kind of overlapping. Your process vision data, whose visual odometry, is now giving you speed, acceleration, and things like that. But you're also getting some position based on your mapping and where it knows it is to combine with your GPS. So it starts to refine that estimate of, oh yeah, this is where I am, this is where I'm going. So, and now we can update our little comparison of navigation methods there and go at the bottom, you know, vision-based navigation, rich environmental understanding, and works without external signals. But it's sensitive to lighting and weather, you know, this is something that I've seen in some of the self-driving cars of, you know, some of them are like, I want to use just optical or just radar, and that can result in situations where, you know, if you're driving down the road, if it's raining, you're not seeing nearly as good as you probably want these things if you're like me. And the car suffers from that too. That's why you have to have things like, you know, the radar and the LiDAR-based stuff that bypasses that. It requires a lot of computational power. I don't know if anyone here has actually tried to run, you know, some vision processing before, but it's hard. It's hard both academically, but it's also very computationally expensive. I usually have to run like NVIDIA Jetson boards, which can cost, you know, thousands depending on which ones you get, and they're heat sinks too. But you're not running that on like an Arduino, not easily. And challenging in textureless or dynamic environments. So I guess if you're in the most bland room you could possibly imagine, you know, there's no features, there's no colors, it's just, you know, that really nasty beige color that this is all around you. It's gonna be hard to get features out of that. So something I want to do with this one too, to make it a little bit shorter but a little more interesting, is I want the question section to be a little bit longer because I've worked in this field a lot, and I think that it might be beneficial if people have questions about this and have discussions about what I just do with all y'all. Like I said, I've been doing this for over 5 years there, and you know, I've been taking classes on it, I've worked in this, I've worked on, you know, air, land, sea, ground mounted, I've done space, I want to do space, various applications, so you know, very interested if there's questions, you know, to continue this dialogue there.
What? Send it back to the first slide real quick.
This one or the other?
First one. All right, while he's running through the presentation, let's hear it up for Sean. You can pick in the question section, but for anyone who's a late arrival, please sign in there. It'll be very helpful. Again, for anyone who didn't hear, if you sign in here, then there's also an exit interview. It's also very brief. We'll send you slides and other pertinent information. And you also get access to the HKN GitHub, which has previous talks and sims that Sean has done. I highly recommend his guidance, navigation, and control sim. He also has a machine learning sim he did last semester. But the GNC one takes a lot of stuff from here, implements it, and lets you actually fiddle around with code and see how it would affect you, control loops, that kind of stuff.
And if you found this interesting, I am teaching the automated target recognition, I guess, in 2 lectures there, which that follows some of these concepts of the computer vision, and you know, takes the bounding boxes, and you know, I'm going to talk about how you really detect that and how you track that off frame, and you know, how you start to really follow that. You know, if you are a device that needs to follow people in a time-sensitive application.
And then so looking at that one. Right.
Oh, it's so difficult to look at.
All right, and then everyone who hasn't yet, which is everyone, please hit that one up. And and once that's good, we can hit all the questions. I highly recommend that somebody asks him to go back through the Kalman filter with the numbers again, just to drill it in everyone's heads. I cannot express how important that single concept is.
Yeah, that is, if anything you do with navigation or sensors is probably going to touch a Kalman filter in some form. If you don't do it directly, it probably has been implemented by someone in your organization and you've been given the code. But that, you know, it's kind of like the PID controller. You know, you're going to see that. You're not going to escape that. You know, if you go into navigation, you're going to touch particle filters too. You're going to touch all of that, but the KF and the EKF, that's going to be part of your life. And it's not, the intuition is not that bad of it. It really is just, you know, I think I'm here, am I actually here? And then, you know, just refining that over time. It's just the mathematics of it when you get to, you know, something with like 20 sensors. It's like, oh, here's like a 30 by 30 matrix, and then here's the Jacobian of that, And each one of those indices is now its own function of, here's a complex derivative, a differential equation, and that just gets nasty. So, but yeah, who wants to roast me or ask questions?
I had a question about the common filter because you just mentioned that it's kind of close to PID controllers, right?
It's adjacent to it. You would definitely want to. It is not quite the same concept, but it would be the next step of if your whatever you produce as a solution out of your navigational filter, common or otherwise, would then go and become a set point to a PID controller. So if it kind of said like, okay, I'm here, my state says I want to be here. It tells you I'm here, and if you tell it I want to be over there, but that's kind of your feedback loop now, and then you can kind of push that toward your plant model, to your actual controller that says, okay, spin the car wheel, move the control surfaces on the plane, that type of thing. So but it is similar. It is another recursive, feeding back into itself there. So.
Okay, so it's rather like a data input rather than an actual controller itself.
That's why when you see this, you always see you see GNC, guided navigation and control, because no matter what you do, if you're a navigation engineer or a controls engineer, you're going to know bits of both, and you're going to do both in some form there. You might be specialized in doing hyper complex extended common filters, but you're still going to know how to solve like a control loop there, how to do coding plots and do all of the stability analysis and all that. But it may not be your focus to go like, oh, I'm going to solve a higher order sliding mode controller. That may not be your skill, but you're going to know what that means in some form. Or that's been my experience at least. But people do tend to like specialize. If they get to like the PhD and like the SME level. So that's a good question.
Actually, I kind of have two questions.
Okay.
In the beginning, when you were kind of talking about the flow chart, you're looking at the Kalman filters. Why do we actually, like you were talking about, it's easier to implement a low pass before you enter in the data? Why do you care about doing that?
Because the low pass can keep disturbances on your sensors from, if you think about like, what a low pass filter does, it's kind of similar to like an averaging filter.
Mm-hmm.
So you can sit there and go, oh well, I have sample, and then something that was anomalously high, and then sample. That kind of stabilizes that out, because if you start going your filter and going like, okay, this is raw data that's fluctuating up and down. You don't have anything on your voltage lines to stabilize that. There's just the wind's hitting it. You're not getting necessarily your true. I'm going this way. You're kind of getting all this jitter and noise, and it is sensitive to noise. If we go back to this here, so this is kind of your presumed noise in your system, in your model, and you make an assumption you're going to have some, because heat exists, wind exists, gravity exists basically. But if you look at this, we kind of neglected this and just said, we live in the perfect universe where noise doesn't actually exist, but it does, and that factors into your state and your model. So, if you can use that low pass filter to kind of go, hey, minimize this, then this model becomes more accurate, because this is going to be another vector, another matrix, another vector that's going to sum into this. So when you start getting into this there, it's like, oh, there's supposed to be a W term here. Your initial conditions would not necessarily be straight ones. They'd be 1 point, or they could even be 2s or 3s, and that's going to cascade down into here, and it's like, oh, now this becomes way off. Now you're summing this, and now this is not nearly as precise as it could be. So that's what the low pass filter is kind of. I had that somewhere. What was that slide? That's the point of this. There is just to make what's coming in, because you want purity of data. You want your data to be as clean as you can. That's kind of a rule of thumb. So that's kind of the order. It doesn't have to be a low pass filter. It could be a band pass. It could be a high pass. I mean, it depends on what your application is. It almost never, as a rule of thumb, hurts to have a low pass filter somewhere in your control loop. Like, that's just kind of something that I've never seen anyone, unless you just make it really coarse, that's almost always a good thing. So, that's why I put that there.
Okay, and then my follow-up question is kind of switching gears. When you were talking about the example of, you may not know it just specifically, of talking about taking the actual plane basically doing GPS jamming and basically able to do vision based and
Mhm.
have it essentially orientate itself that way. Was that only using vision based, or is that using any kind of onboard IMU or any kind of?
So there was some, you from the Lidos example there?
Yes.
Yeah, they had, it was a sensor pod on an aircraft, and it had a variety of, options, including GPS, and it had, IMUs there, too. But, so it would do its own, orientation, but it was the SLAM algorithm. It was the mapping of like coming out there and figuring out where it was, tracking that with GPS, and then when it came back around, it would go, oh, I don't have GPS anymore, but I've seen this picture before.
I see.
And then it could kind of like, because it would be coming that way and then coming back through, it could kind of reorient that and go, okay, my map says I'm now here, and I'm oriented a different way, but I know when I do all that and do the homography and all the angles and all of that stuff, that I'm where I was, some number of hours ago. But the IMUs can do it too, when you get to some of the military grade IMUs, the stuff that they use on submarines that cost, hundreds of millions per chip. Those can go without GPS for like 6 months to a year or something, but they're designed to. They go on like a nuclear submarine, right?
Yeah.
But the cheap ones you buy like for Adafruit, last you like 6 seconds without before they start drifting or something. But for most things that's fine, But that's the thing is you can with techniques like this you can kind of get around that. I mean, you could easily just put 6 of them on the plate and just say fuse all that, and then it's the redundancy thing. You can start to like improve those just by doing more of them in a scheme like this. So,
Is there a point where you kind of have to consider like marginal benefits of going with more information?
Yeah, definitely. If you do something like this, your model comes into play there. If you think about like this there, this is 2 sensors in 2 dimensions, so x, y, and dx, y. This is not accounting for acceleration. That would add 2 more to this. So now you're like dealing with 6. Then you sit there and you go, okay, roll pitch yaw, magnetometer information in there, and then you go, okay, cool. And so now you're like at a 20 by 20 matrix, and you go, oh, well, cool. Now you get the vision stuff too, and you have like visual odometry, and you have all this feature extraction. So now your matrix is like, oh, I'm a 128 by 128 matrix there, which I dare any of you to solve that by hand. So, if you have a sensor that's redundant, then, you can, you don't really need it, but something you can do is, so this is the measurement function, so the Kalman filter. This is not necessarily your sensors. This is what your filter is getting as a measurement. Going back to the algorithm here, it's this measurement. So if you know, and I learned this reasonably recently, if you know that, say, this is getting your, say, velocity arbitrarily there, and you know your velocity is in 2 dimensions here, it's in x and y, but you have like a bunch of sensors doing that, you can start to kind of like reuse some of these measurement functions. You really shouldn't, because everything should be unique, but you can make some assumptions and generalize things. You lose some of the uniqueness in there, but you have 10 sensors and they all roughly have this. You can kind of do some tricks like that and keep your model simple and just kind of keep polling that type of thing with a different line. But yeah, more is not always better from a computational perspective unless you can find a way to reduce it. But because this is all recursive, it's mostly a forward processing issue. It's not like oh, I'm storing the last 100 states, and that's eating up memory. It's like no, you're getting last time step and then now. So it's very efficient from that perspective, but if you are solving a 256 by 256 matrix, that's always going to be slow, but because we have graphics cards now and we have embedded system on-chip computers with graphics cards and CUDA processing, you can actually kind of start to, you put in a matrix, it gets faster. That's another rule of thumb. When you're doing stuff like this, don't do this in a loop. Don't iterate over a loop. Like make this a matrix. Do the matrix map, like in code. Use like NumPy, use Glass, use something that you can put on a graphics card. Matrix map is faster than just iterating over loop there. Put it in one loop, do everything, do matrix map. You're gonna be happier, you'll run faster. But I guess the real answer to that is probably, I hate to be like it depends on the problem, because I had professors that did that to me and it made me want to strangle them. But it really does, like, sometimes it's good to have that data, sometimes it's not, because it is, if you're too precise, right, you may not care about everything. It's like, I think the analogy I would use is overtraining in machine learning, if you're familiar with that there, where you basically train it on too much of the same data, so it loses the ability to generalize. Sometimes too many sensors, you get snowballing, basically. It's like, oh, I have too much there. So, I guess yes and no, And that's the art of this, and the art of Kalman filtering is figuring out what you need and how to model that, and that type of thing.
So it depends kind of on the situation.
I think so. I mean, in general, I think though having more sensors and more data available is, because you can't always just not use data. Like you have like 100 sensors and you don't have to sample all of them. You can turn them off. You can just say, I collected this and just not throw it into your filter and just, store it, log it, keep it as metrics, When you figure out your thing crashed, the 8th order vibration is what actually caused it to crash, that's like, oh, well, at least we have that data now. Because sometimes that's all that is. It's just, I've seen that in control loops of, like, oh, here's like a 5th order term there that caused an oscillation that resulted in something, flailing out and hitting the ground at an angle that it really wasn't supposed to ever fly at. So, but yeah, hopefully that made some sense there. I think there's a question in the back, maybe? No?
No, I'm not ready.
Anything else? Anyone else? Okay.
I have one last question. From like the standpoint you said of like having multiple sensors or like devices that like data needs to go to and whatnot through the controller and stuff like that, how often do considerations of like what's happening on the actual like lower end like OS coming into the picture, like with threading and like multiprocessing and stuff?
I mean, constantly. This is I've done a lot with software architecture and some distributed systems, things like that, where you do have real-time sensors. In general, my experience has been I like to personally spin off anything that is sampling a sensor into its own space. Because if you think about, because all it takes is something hanging up there, and then like your temperature sensor is responding slow, and now your like speed sensor is like not keeping up with what you actually need. Especially on systems where you might be sampling something that your temperature at 1 hertz, but your encoder at 40 hertz, right? Or something like that. It also matters because this is thinking about just running, like for example, like just a off-the-shelf Linux distribution. They make low latency kernels. There's things like real-time operating systems that bypass that even further and try and separate things out into channels. You also get into the FPGA type space there where you're getting just hyper specialized and super fast. And the main thing for that is the ability to sample more than like concurrency matters, but the ability to just sample things faster. Because if you look at like a lot of sensors, I've seen lots of cameras that'll be like, oh, I'm at like 50 hertz or 60 hertz there. It's like, well, most programs are not going to want to run that way, especially computers. But you can get into specialized, OSs and hardware that will let you process that, filter it down, because what good are some of these sensors at like 60 hertz to the average person? Not that much, but filtering it down, getting all that and filtering it down in a meaningful way is, and then so you can pre-process it further, and that might even go into I swear I know this direction, my notes aren't here. The low pass filter, really that probably should have been like pre-processing of raw data. I almost seldom use any raw measurement data. I don't really trust it honestly without being filtered or something, because all it takes is like, oh yeah, raw data into your your throttle control there, just a voltage spike puts it to full tilt or turns it off, which is something I've seen a few times there. It's scary, like, wow, that just happens now. I had a situation when I was at Kratos where we were testing a motor controller, like a big motor, like a 50-pound motor, like an industrial motor, and we were trying to write a control loop for it there. And this is a good lesson how I talk about this story. It's funny now, but it was nightmarish at the time. But we were trying to do a PI controller for it. And, we had no model for this controller at all there, or for this motor. We were just kind of like, guess and check, right? So, me and my buddy, who I'll preface is still alive and has all of his limbs, but we decided that, okay, well, we need to kind of like hold it a little bit and go from there. It's like, okay, cool. So it started sampling, started doing this thing there. It's like, okay, nothing's happening. So it's like, okay, cool. Increase the integration term there because clearly that's not working. Well, what the controller saw was there was no resistance on that wire that we were holding. So it said, hey, I need to pull on that wire. So this was a 3,000 RPM motor spinning a 40-inch stainless steel disc there. So, anyway, we learned very quickly that steel wire can bend that into a pretzel. So it was completely Pringle shaped there. So, I don't trust unfiltered raw data since that because all it took was like, oh, that's an anomaly, and we had HR coming out asking if we just needed to call the hospital or the coroner. So, very, very terrifying.
Was that phenomenon you're talking about with the when you're increasing the integral terms when it's like the motor itself kind of hits a peak at how the RPM it's able to actually get at, but then the integral is just like, hey, we're gonna keep going until it reaches something.
But it was more of the way the loop is set up. It was like, we want you to go to a speed based on resistance on the motor. Because the motor had some sensor that let it pull on it. It was like, okay, there's this much voltage being returned on that sensor. And it was like, oh, but there's no feedback, so I need to keep spinning. Because we were holding the wire up, so it wasn't taut, so it was just kind of hanging there. So it was like, oh, I have no tension. I need to get that tension going. And so it was like, okay, well, if I have no tension, I'm still seeing that after, a femtosecond, which it was, it just kept going, okay, trying to go faster and faster and faster. And, going from 0 to 3,000 RPM in I think a tenth of a second there was, a life-changing experience there. But since then, I don't trust raw measurement data. I just getting the raw, unfiltered, unprocessed data, especially with control loops. That's, but again, he was holding the wire, but, he let go and no one was hurt. Thankfully, he still talks to me pretty regularly, so I don't know why, but he still does. His wife is a little salty about it. But yeah, I don't trust raw measurement data, and anything, especially at high frequencies like that. So but you do have to consider that both from a safety, but also just a concurrency thing. We also had times with that where it was like, oh, I think I wrote this piece of code that was supposed to sample from a sensor real time some arbitrary hertz, and then pipe it off to a different thread, different process for dispatch into a control loop or into some metrics thing. And that was when I was going like, oh, well, those actually need more concurrency because if you just kind of send things off at rate n and it gets it because the time latency at n+1, you find your control loop is no longer synchronized. I've seen that several times of oh yeah, you send this over and there's just latency in your network, latency in your your IPC or something, and it's like, oh, now this is delayed by one time step, so which you're like, oh, that wouldn't make much of a difference, but that's when things start spinning in circles because it's like I'm not getting the data I think I'm getting, but the data I'm getting says I need to turn left. So and then it gets confused and it does the broken Roomba type thing. But yeah, that is a consideration to have. The speed is definitely one. So that's a good question. I like talking about that subject. I like computational efficiency. So, anything else?
More of an observation or comment than that. It's built into your equation or you built into your examples, but I didn't hear you explicitly state it. And I just wanted to point out that one of the powers of the Kalman is that the errors can be different in the different dimensions. And so when you look at the X and the Y, when you build your covariance matrix, they can be different. So for example, GPS is good in lat and long, but it's not as accurate in altitude. And so you would have a larger error term built into your altitude.
Well, you can kind of see a little bit of that here with the computed predicted states. You can kind of see that the error here is, basically higher than when you start fusing it. But yeah, you're right that, I've seen this when you look at the outputs of a lot of common filters, is you basically can generate error plots that give you, a series of curves that say this is per dimension what you're actually looking at. And that can be helpful when you start actually getting your standard mean and distribution between your curves and go ideally when you start making those, what you want to see, especially for something like this, looking at this one, is this state, in general, I think I see like 2 sigma deviations. So like, 66% some of the time is you're going through your runtime, your model should return states that are, within, so much of the mean of each other. If you're sitting there going like, this next time step, this becomes 11 and that's 30 or something, you're probably way outside bounds. You want to be you can be off, but you won't be like consistently off. You don't want to like, be way off like that, but that's a good point. I should have asked.
It's just one of the most powerful things about the Common there is that you can have the things weighted and you can adapt the weights over the course of the run. Say if you're getting closer in range to something, or it's getting closer to you, the covariance matrix, the error bounds can actually decrease and weight that data higher.
And that's what you see here is the Common gain gets, every recursion will be updated there with its current measurements, its current predictions, the process noise, all of that. So it is a dynamically changing process. It's very organic in that way. But yeah, it's simple to kind of get the intuition of it, but implementing it and doing it, especially for larger models, gets unpleasant. That's where something that has a lot of graphing capability can be useful. So.
And from a design perspective, if you're trying to build a system and you want to try and build up a common filter, you'll need to know these errors. And with regards to getting errors for any given sensor, 90% of the time, you can open its data sheet and its error will be there. And you can just plug that in, and that's great. But if all else fails, you can simply make 100 measurements and then compare it against a source of truth and try and compute your average error.
Excel is very good for that.
Yeah.
You can do a lot of extrapolation of like voltage curves if it doesn't give you that on your part there. But that's where some of this process noise and the measurement noise comes in of like, oh yeah, this is what this is. You know that it's 50% accurate. That's an X and Y basically. And it might even tell you like your X is 50%, your Y is 75%. Why you would make that bad of a chip, I don't know. But it's something that might be there, and it's like, okay, yeah, put that in. But you can also do the measurement and testing, and that's something that they love to give to intern T1 engineers. So the menial task there of just go run it 1,000 times and see what happens, see where it breaks, and then as you get more into your career, you realize how invaluable that actually is to everyone to know when that happens. So. But yeah, no, it's completely right. That's, knowing those curves and responses, if you're doing it as a system designer, the new design stuff, it's going to break more than it works. That's just, I don't know if anyone here is connected with the Space Hardware Club, but that was a good lesson that they taught when I was in the club there, that most of the time stuff breaks, usually spectacularly. But I wasn't in rocketry, so I didn't even see anything explode. Balloon stat represent.
And as a rule, as you go through your life, as Sean mentioned, these things are better the better your model is. And models, like if you like a certain sensor, like you really like this cheap accelerometer you can get off Amazon, and over time, you use in a lot of projects, you can get a bunch of data and build better and better models of it. That allows you to later on, fresh project, you can slot in the exact same model for your sensor. Models are not filter by filter dependent, they are sensor to sensor dependent. So if you build out a good library of models, or find them online, they exist. But if you build out good libraries of models for yourself, that's basically like a tool you keep forever and allows you to rapidly advance your projects and developments over time. Because you basically common filter, if you have all the numbers, 5 minutes, it's done, it's ready.
And if you really become good at one, like redundant fusion gets on the table. If you have a sensor in and out, like a AXL 900 or whatever that little IMU is, if you know that back and forth in every aspect of that model, get multiple of them and do something like this. That's on the table. I've seen people, especially in the field of like electro-optics and cameras, come in and be like, well, what's your focus in your career? It's like, I know like FLIR cameras. Like FLIR boson, that's my thing, and then it's like, and they're like, okay, here's 200K right there. It's if you're good at that and you know that, that's the ability to come in and quickly do that and get that data and be optimal. I mean, that's invaluable. But yeah, just doing stuff with, cheap things and modeling that will, it's great to learn, but you should never discredit the power of cheap hardware. Like that's a good teaching point. You should, you should respect that you're not gonna get the best thing, but you should appreciate that you can do a lot with stuff that's functionally disposable, especially in like electronics and software and maybe not mechanical as much, like if you buy really bad metal that bends and breaks, that might be a actual problem, but if you're doing some electronics, Amazon has some great, give me like 20 of a sensor for $9 from, a sketchy warehouse in China type thing. Big fan of those.
We've reached a world where a missile no longer costs $1 million. You can probably make it for 200 at your house. Not half.
He's a patriot though.
I'm an American. I think there's a question.
Someone? Yes.
Do you have any recommended resources or like classes that you think would be very helpful to getting more knee deep in the subject?
Real quick for the classes. In the electrical engineering department, there are graduate courses specifically on common filters.
Yeah, there's a common filter class. Who teaches that? Is it the radar guy, isn't it?
Lawrence?
No, the other one.
What?
Yeah, like the dynamics guy, I think.
He was on.
Yeah. No,
Dr. Buzz?
Yeah, it might be. But yeah, there's a KF class. There is a navigation theory class that they taught last summer. No, summer before last, I guess.
That was an Air Force guy?
Yeah, he was the Air Force guy, but he actually works in my old group at Leidos that did division navigation. So he had a lot of, and he did, gravity navigation and, like a magnetosphere navigation, new stuff like that. That was a really cool class. It was very hands-on. He had some labs, how does it go and like collect real world data and make common filter and particle filters out of it there. It was a special topic, I think like a 601 or something, but it was a pretty cool class. Outside of that, I'm trying to think of like what, I started in system theory and controls and went from there and went into robotics and specifically drones and UAS type applications. And that kind of just, people just go, oh, you can do a control loop and you like drones and robotics, navigation becomes something they just give you and you kind of pick it up like that. There's a lot, there are some good YouTube channels. I'm trying to think of,
I think 3 Blue 1 Brown has a
yeah, 3 Blue 1 Brown has several, there's several of the Latvia systems that guy.
I don't know if you want to send it to the missile guy.
He does navigation and controls. Some of those guys that do like amateur rocketry on YouTube get into, here's like applied navigation into something, rocketry related. I endorse nothing they do, but they are smart guys. And some of them are professionals too, so, I really, at the end of the day, especially with something like this, and this is the fun part I think of electrical engineering, is you don't actually need that much money or resources to just go and like do this. You're not making a wind tunnel, or a radar chain or cough. You can go get a Raspberry Pi or a little Adafruit GPS, Adafruit IMU. You can implement this in C++ or Python, you can search out just a very basic thing there and put that, with some wheels on a little car and just drive it around, or even just hold it around and just kind of rotate it and see as it tries to predict where it's going. So under $100, you go down and get a parts supply probably and buy all the parts to do it. So that's kind of the nice thing is if you want to do it, you can kind of just do it. Again, chilling with the space hardware club there, I learned a lot of what I do, sitting in the lab at midnight there over summers, trying to figure out why this wasn't working because there was no instructions. It was just like, we need this to fly, so it needs to fly some way or another. And that's how balloons were lost. But yeah, so I mean, again, my advice is always just if it's not going to like cause legal or harm to people, just try it. And financial harm too. Don't buy like the nicest hardware and deliberately blow it up. But that's again, hardware can be cheap. If you're going to do something on a test drone or a test vehicle that's You know, you're like, I just need an IMU. Don't get the one that costs $1 million. Get the one that costs like 100. You know, and make the assumption that it's not coming back. Because it usually isn't.
Well, way back, even predating me, there was, from one of the primes, there was a little pamphlet that was written that was, you can probably guess the era if you're a movie buff, that was entitled How I Learned to Stop Worrying and Load the Common Filter. And you can probably find bootleg copies of it online, but it was, I want to say like North American Rockwell or something like that, so it has been merged through 14 different acquisitions. But it was fairly thin, probably about 20 pages that kind of filtered the mathematics into a more intuitive and understandable.
So this was my first exposure, and this is it's not my computer. This guy has a book there, but this is I worked with, I guess, when I finished undergrad, when I was going into the workforce and kind of into controls and navigation. But he has a book you can buy too, but he gives you like really good examples, and I guess now he goes into like nonlinear approximations there, so there's that there. But this side, the common-filter.net there, he goes into like the basics in pretty good explained ways, and he even goes into like he has like problems you can solve with it there, but it tells you the value of precision versus accuracy there. Which you want this, you want the precision accuracy, but you don't always get that. But I used to have more of his book, online, I guess. This might be it. Yeah, what he talks about. Yeah, so he talks about this and talks about, hey, measurements, estimates, true value, and all of this there, what 10 measurements of this looks like, state predictions, all of this there. But this site, this common-filter.net, highly recommended. It's a good starting point, good intuition. I sat down at some point, like I said, when I finished undergrad, I graduated during the COVID year, so I probably did it when I was stuck inside. And just did his problems in Python and see he gives you like different equations to do stuff there. So he does the Coleman game for this, the covariance updates, state updates, extrapolation, all that. But this is a good site, and this gives you some good starting points to, make one for yourself. If you do make one, like I said, the models get complex, so, don't start out going, I'm going to fuse every sensor in my electronics toolbox. I mean, it's probably a good learning experience, but, it may not work. You may want to just do like, the two-dimensional. And the other thing you learn with this is the assumptions you can make. It's physical modeling, right? That's all you're doing. You don't always need to model acceleration to get an accurate navigation result there. I mean, you can make assumptions about some of these like physical attributes and what your system is saying. You should. I mean, you should always have the most accurate real-to-life model, the known universe everywhere. But you also don't need that in a lot of times. You can reduce things. You can consider something as I care about my position. What do you really care about your acceleration to get there, or can you assume it's constant? Thinking of like the free body problems that we all did in physics at some point. But yeah, this side is pretty good there on top of. There's a lot of literature about the Common filter. I didn't know that he had like the time of it when the guy was to give a date. But this guy was around from 1930 to 2016. Yeah, okay, 1960s. So that's how far this goes back. So there's been some time when people really think about this, as far as improving it and proving the mathematics work. So stuff to consider. But any other questions? No.
Another round of applause for Sean. Thank you everyone for coming, and for those who came in a little late, we have 3 more talks this semester. They are every 2 weeks, Thursdays, 7 p.m. This one got pushed back a little bit. 7 p.m. in SST 150, same floor here. We have electronic warfare is next. Then Sean's coming back to do automated target recognition and tracking in April. And then the final talk of the semester is stealth design principles. And for everyone who filled out that form, we'll send these slides out this evening.